In the earlier modes of heat transfer, namely conduction and convection, there is matter prevailing. Whether in conduction or convection, in the conduction it is the molecules that are vibrating, lattice vibration, etc., and free electron transfer, whereas in the case of the convection there is a macroscopic displacement of the fluid naturally or artificially by an external agents. But in this third mode of heat transfer called radiation, there is no matter prevailing. It can happen even in the vacuum. In fact, we receive the heat energy from the sun to the earth by radiation phenomenon only, which happens by electromagnetic waves, which propagate with the speed of light. So, I can say radiation is the mode of heat transfer which does not require any material medium, that is, it can happen even in vacuum by electromagnetic waves propagating with the speed of light. If you look at the electromagnetic spectrum, thermal radiation would occupy a wavelength of 0.1 microns to 100 microns. 1 micron is 10 power minus 6 meters. So, thermal radiation would happen in this wavelength zone. Lambda is the wavelength. So, in the electromagnetic spectrum, thermal radiation occupy a wavelength band of 0.1 microns to the 100 microns. All high temperature bodies emit thermal radiation at very short wavelengths. Example, sun's radiation. All bodies at all temperatures emit radiation, but a high temperature body emit thermal radiation from its surface at a very short wavelengths, whereas a low temperature body will emit radiation at long wavelengths. Sun's radiation is a short wavelength radiation, whereas any earthbound radiation or low temperature radiation is a long wavelength radiation. So radiation does not require any material medium. I can give the very best example for the radiation. If we are sitting in front of a forest fire in a very cold, chilly midnight, forest fire is there in front of us, but surrounding air is very cool, taking heat by convection from our body, but still we feel very warm. Why? Because the hot flame in front of us will be emitting radiation energy to our body, which will be compensating the heat lost by convection from our body to the surrounding cold atmospheric air by convection. The heat loss by convection from our body to the surrounding air is compensated by the heat what we receive from the hot flame by the electromagnetic radiation heat transfer phenomena. In any particular heat transfer problem, all the modes of heat transfer would simultaneously prevail: conduction, convection, and radiation. But radiation would dominate over conduction and convection, particularly when the temperature difference between the hot body and cold body is very high, that is in the order of 1000 degrees centigrade, the radiation would completely dominate over conduction and convection. They become minimal. Radiation would become very predominant portion. It will contribute predominant heat transfer portion as compared to the conduction and convection if the temperature difference is very high. For example, I can give heat transfer between hot combustion flue gases and the refractory walls of a large power generation boiler is predominantly by radiation, and a small fraction may be by conduction and convection, but it is predominantly by radiation due to, the reason is due to very high temperature difference. So whenever the temperature difference crosses 600 or 700 degrees centigrade, the radiation immediately dominates over conduction and convection. At moderate temperature difference, conduction and convection will dominate the radiation. So in any heat transfer problem, all the three modes of heat transfer would simultaneously be prevailing. So based on the what will dominate over the other, we will be solving the or analyzing the problem. Now, having seen the three modes of heat transfer, namely conduction, convection and radiation, now let us discuss about the governing laws of heat transfer, namely Fourier Law of Conduction. First of all, let me state the law. The law states that the rate of heat transfer by conduction is directly proportional to the temperature gradient and is also directly proportional to the area of heat transfer lying perpendicular to the direction of heat transfer. Representing pictorially the Fourier law, that is, let me consider a slab of thickness B. This is high temperature surface. This is low temperature surface. Heat is conducting in this direction, x direction I say. This is the x direction. Here x is equal to 0. Here x is equal to plus b. Qx is the rate of heat transfer flowing from high temperature T1 to low temperature T2. I shall represent the temperature variation like this. with respect to the, so t is a function of x. At x is equal to 0, t is equal to t1. At x is equal to b, t is equal to t2. T1 is greater than T2. The heat transfer is taking place from high temperature to the low temperature. So according to Fourier law of conduction, Qx, the rate of heat transfer by conduction, is directly proportional to the temperature gradient dt by dx. What is dt by dx? If dt is the temperature drop for a distance of dx, dt by dx is the temperature gradient and directly proportional to the area of heat transfer A. So Fourier law could be stated as Q is equal to minus Ka dt by dx, so many watts. Why the minus sign? The minus sign shows that as x increases, temperature T decreases. That is, heat would always flow in the direction of downhill of temperature according to Clausius statement of second law of thermodynamics. K is the thermal conductivity of material of slab. This is the Fourier law. Now coming to the second governing law for convection, namely Newton's law of cooling for convection. Each mode of heat transfer has got its own law. Newton's law of cooling for convection. K is a please note that earlier I had defined K, which is a property of material. Of course, K is not a constant. It may be a function of temperature as well. I would rather discuss about variation of the K with temperature later. Now, first of all, let me elaborate about Newton's law of cooling. The law states that the rate of heat transfer by convection between a hot solid body and the surrounding fluid is directly proportional to the temperature difference between the solid body and the fluid, and is also directly proportional to the area of exposure or area of contact between the solid body and the fluid. For example, if I take a plate like this, hot plate, over which a fluid, air for example, may be blowing over the plate. Hot plate is at a temperature of Tw. Air might be at a temperature of T infinity. Tw is greater than T infinity. There is a convection heat transfer, Q convection. A is the surface area of contact between the plate and the air, I suppose. Now, according to the Newton's law of cooling, Q convection, that is the rate of heat transfer by convection, is directly proportional to the Tw minus T infinity, that is temperature difference between the plate and the air, and is also directly proportional to the area of exposure. The proportionality constant I can put with H. So HA delta T or HA Tw minus T infinity. Here Q convection is the rate of heat transfer in convection. The amount of heat energy convected per unit time is Q convected. And H is the convection heat transfer coefficient or film heat transfer coefficient. In the units of H or in watts per meter square Kelvin. This H is not a property of material nor property of fluid, but in forced convection H is a function of velocity of the fluid, characteristic dimension of the solid body, density of the fluid, dynamic viscosity of the fluid, specific heat of the fluid, and the thermal conductivity of the fluid. These four are thermophysical properties of fluid. Rho is density of fluid in kg per meter cube. Mu is dynamic viscosity of fluid in Pascal second or Newton second per meter square. It is a property. The viscosity is a property of the fluid. Cp is specific heat of fluid in joule per kg Kelvin, and K is thermal conductivity of fluid in watts per meter Kelvin. V is the velocity, free stream velocity of fluid, and D is the characteristic dimension of solid body. In the case of plates, it is the length of the plate lying parallel to the direction of velocity of fluid. If it is in the case of a hot sphere, the diameter of the hot sphere we would have to take as a characteristic dimension. So based on the orientation and the shape of the solid body, the characteristic dimension is decided. D. Now in the case of free convection or natural convection heat transfer, H is a function of G beta delta T L mu rho, Cp, K. The last four are again thermophysical properties of fluid which is receiving or giving heat by convection. Coming to the G, this is acceleration due to gravity in meters per second square. Beta is isobaric thermal volume expansion coefficient, which is defined as change in volume by original volume divided by change in temperature, or dou V by dou T divided by 1 by V. This is per Kelvin, having the units at constant pressure. Isobaric means constant pressure. Delta T is the temperature difference between the plate and the fluid, and L is the characteristic length of body in meters. So in the case of free convection, there are many more properties that are deciding the value of H. So as a whole, I can see that H is neither a property of the fluid nor the property of the solid. It is a composite property. Now coming to the law of radiation, namely Stefan-Boltzmann law of thermal radiation. In fact, there are many more laws of radiation, namely Kirchhoff's law, Wien's displacement law, Planck's law, etc., Lambert's cosine law, etc. Stefan-Boltzmann is the prominent among all the laws of radiation because this tells about the rate at which heat energy is emitted from the surface of a black body. Black body is a very important concept in the thermal radiation. How do you define a black body? Black body is the body which absorbs all the thermal radiation incident upon the body. It doesn't reflect anything. A body painted with a carbon black, which is used as the absorber plate in the solar flat plate collectors, could be visualized as a black body. Now coming back to the law states that the rate of radiation energy emitted from the surface of a black body is, from the surface of a black body per unit area is directly proportional to the fourth power of absolute temperature of body. Mathematically speaking, that EB is directly proportional to the T to the power of 4, where EB is the emissive power of black body. B for black in joule per second meter square or watt per meter square. The energy emitted per unit time and per unit area is known as emissive power. The emissive power of a body is the energy emitted per unit time and per unit area. T is the absolute temperature of body, black body in Kelvin. Whenever we deal with the radiation phenomena, please write the temperatures only in Kelvin scale or thermodynamic temperature scale or absolute temperature scale. The proportionality constant could be known as sigma is Stefan-Boltzmann constant, 5.67 into 10 power minus 8 watts per meter square Kelvin per 4, which is one of the important universal constants. Stefan-Boltzmann constant is a universal constant. Now, having seen the three modes of heat transfer and the individual laws that govern the modes of heat transfer, now I would consider the very important case, namely case 1 of unidirectional or one-dimensional conduction heat transfer, steady state through a solid, through a slab. And let us integrate the Fourier law. This is Qx, rate of heat transfer. This is high temperature at T1, the surface low temperature at T2. B is the width of the slab. This is the direction of x. This is the temperature variation, slope of the temperature variation. dt by dx, dt by dx is temperature gradient. Now, I assume that steady state heat transfer means the temperature of body at any given location would not vary or change with respect to time. T is function of x only. It is not a function of time. Here x is 0, here x is plus b. Now, taking the Fourier law of conduction, Qx is equal to minus Ka dt by dx. I assume that K is also not a function of x, or K is not a function of temperature. It's not a function of temperature. K is constant. So, there are two variables now in this equation, that is T and x. Separating the variables, Qx into dx is minus Ka dt. Integrating both sides, integral Qx dx is equal to minus of integral Ka dt. The limits of x are 0 to b. The respective limits of t are t1 to T2. At x is equal to 0, at x is equal to 0, T is T1. At x is equal to B, T is T2. Heat transfer is from hot surface at temperature T1 to low temperature surface at T2. Because temperature cannot be a function of time, Qx cannot be a function of x. Because if you take a differential strip of width dx, if Qx is the heat conducting into that element and Qx plus dx is the heat conducted out of the element, dx is the width of the element, small differential element considered in the slab, Qx must be equal to the Qx plus dx for steady state heat transfer. Why? If Qx and Qx plus dx are not equal, then there must be some heat left out in the element, which would increase the temperature of the element from time to time, because we had assumed that steady state heat transfer, that is temperature, cannot change with the time. Qx and Qx plus dx must be same. That is, Qx cannot be the function of x to satisfy steady state heat transfer condition. We had already assumed it is a steady state heat transfer. So, separating the variables and taking the constants out of the integral, Qx integral 0 to b dx is equal to, k is also a constant, k minus k t1 to t2 a dt. After integrating, we would obtain Qx into b is equal to ka t1 minus t2. That is, Qx is equal to ka t1 minus t2 by b. This is the formula for steady state heat transfer rate, one-dimensional heat transfer rate through the slab. If k is variable, if k is function of, if k is function of temperature, then variable thermal conductivity case given as k is equal to k naught into 1 plus or minus alpha t, where alpha may be a constant. In such case, we would have to take the function of k into the equation and then we have to integrate the function, taking the variable thermal conductivity case.